This is Fundamental Problem 1 from Chapter 18. The 80 kilogram wheel has a radius of gyration about its mass center O of 400 millimeters. Determine its angular velocity after it has rotated 20 revolutions starting from rest. So in this problem, we're going to use the work-energy relationship. So in order to do that, I have to figure out the kinetic energy initially and finally. Initially, it's at rest, so T1 is equal to 0. And for Chapter 18, for the kinetic energy, I can either use formula equation 18.6 or equation 18.7. Remember, from this formula here, you can either do the moment of inertia about the instantaneous center, or if you have a fixed point O, you can do the moment of inertia about that point, and that's the total kinetic energy. So T2 is equal to 1/2 times the moment of inertia about O times the angular velocity. That equation was in your book earlier, but I did not put it on the equation sheet. That is equation 18.5. You can add it to your equation sheet if you want, or you can just say point O is an instantaneous center of zero velocity and use equation 18.7. For the moment of inertia about O, they gave me the radius of gyration about the mass center O is 400 millimeters or 0.4 meters. And then remember, in equation 17.5, the moment of inertia is the mass times the radius of gyration squared. So we have the moment of inertia is the mass times the radius of gyration squared. The mass is 80. The radius of gyration is 0.4 meters. And, well, I don't know what that is. So we'll just say 1/2 times 80 times 0.4 squared times omega squared. And also I need the work. Now, rather than using equation 18.4, you could use equation 18.18, but in this problem, the change in potential is 0, so the height of the mass center is not changing, so we have no change in gravitational potential energy. There are no springs in this problem, so if we use equation 18.14, we don't have any work done by the force of gravity anyways. So let's just do that and say T1 plus the sum of all of the work is equal to T2. Okay, so gravity doesn't do any work in this problem because the height of O is not changing. O is the mass center. And so the only other force that we have is the force P. That does do work. And the force P is constant. So when you do the integral here, you can pull out that force. And the displacement at this point is in the same direction as the force. So it's just F times ds. It's cosine of 0 degrees here, since the displacement and the force are going in the same direction at this point here. So for the work, we have pull the force out. The force, let's call it P. Pull it outside the integral. Then you do the integral of ds. But I don't want to integrate with respect to s here. I can use the formula for the arc length to say ds is equal to r d theta, and then r would be the radius that we have here. That's not changing. You can pull it outside the integral. You can integrate with respect to theta instead, from the initial angular position to the final angular position. Now, we are looking for omega after 20 revolutions. So if we start at 0 after 20 revolutions, theta 2 is going to be 20 times 2 pi. So this is P times R times 20 revolutions times 2 pi for the change in angular position. Okay, so now I can go ahead and plug everything into my formula here. So T1 is equal to 0. My work, since the displacement and the force are pointing in the same direction, the work is positive. That's P, which is 50, times R, which is 0.6, times 20, times 2 pi for the change in angular position. is equal to 1/2 times 80 times 0.4 squared times omega squared. We solve for omega, and you get 1200 times pi divided by 6.4, which gives you 24.3, and this is angular velocity, which has units of radians per second. Notice that when we did the work here, that looks like what you have for the work done by a couple moment, so it's the moment integrated with respect to theta, and that gives you the same thing. Okay, so that concludes fundamental problem 1.